So with respect to these three, more or less three big concepts, there are multimodal data, ensemble learning, and feature selection. Currently, our feature extraction package is not released, and we're still working on it. But we have been applying we have been experimenting and actually applying these methods and on multimodal data sets, and also in the ensemble version. So I'm going to show you two examples of how, say, not really the workflow of how we carried these experiments, but sort of that you get the idea how the code looks like, and if you want to reproduce the same thing because you happen to have a problem that looks similar to this. A problem with the data is multimodal, say. And these two examples talk about different type of data. One is about time series, like NATOPS. And so with respect to NATOPS, maybe there is a big difference in what I'm going to show you in terms of the nature of the data. So let's take this first example. So this is a data set of 198 patients that have been, not patients actually, people staying at home during COVID time that downloaded an app and were asked to record the cough and breath events, essentially, and were asked if they had COVID or not. So each instance is described at the same time by a cough event, an audio of a cough event, a recording, and a breath event. Okay. And for example, here we have many temporal points for this audio. An audio is nothing else than a univariate time series where you have some pressure, some mechanical pressure hitting the microphone, mechanical waves distributed through time. However, in signal processing, it is very, very common to extract frequency information from this kind of data. And in this example, I present the data to you in a way that this was already done. And from this audio, 13 different temporal variables were extracted. So you get a time series of, this is a parameter, we chose 30 because it's apparently what, close to what is usually used in the literature. And each variable measures how much a given audio frequency was present at any point in time, okay? So if I cough and I record it, I can decompose using Fourier transform-based preprocessing. I can decompose how different frequencies in a given range that is parametric that I choose and is distributed in a way that that was studied, distribute throughout time, right? And I do this with both cough and breath audios, so that essentially I have two time series for each patient. And of course, the task is to recognize whether the patient is negative and positive. In the work that we did, we achieved high accuracies, higher than, around 95. But there are many different ways in which you can pose, in which you could pose this problem given the data that we were given. It was not just one data set. I'm taking a specific data set where, for example, the negative are a non-smoker, have no asthma. So, but yeah, and all I'm saying is this is just one out of many data sets of such kind, and apparently these models, and especially in their ensemble learning version, modal random forests, did quite good. In what I'm going to show you, for time constraints and also the fact that Jupyter Notebook, I think, adds an overhead whenever I add an experiment, so the kernel usually crash, we are going to see a lower accuracy, maybe smaller models. So it's a toy example just to show how to handle multimodal data. Okay, and with respect to what we to what can be done and what could be done in the future, I'm skipping the feature selection and analysis of the data steps. So if I load the data now, I have two tables, of course, and since in Julia we couldn't find a way of representing model data in this clear way, where you have what is a multimodal data set, if not like from a structural point of view, if not two tables with the same number of rows referring to the same object, you know, the same patient in this sense. So apparently we had to build something that essentially is a wrapper for a vector of data sets. So yeah, there is no magic in there. We call each of these the modalities of the data. No, it's not we call, I mean, the literature calls it like that. Yeah, so in this case, I have two modalities, the cough and the breath, right? So this is an example. I'm showing the cough modality. If I plot, say, these are 3 positives and 3 negatives, okay? This is how they look. So I have around 90 temporal points, and this is how the different frequencies distribute. You know, I've shown in NatOps you could guess that it was some kind of simple thresholding would suffice, but in this case it's more difficult. So I would argue that in nature this kind of data is different, is more continuous in a sense. Also, yeah, there is something harder with this data. Well, of course, we have many points. Maybe it's also the fact that it was processed in a more complex way by this Fourier transform pre-processing, which, by the way, is a step that, importantly, for the kind of experiments that we do, is interpretable. I mean, it is functional. You take the audio and you decompose it, but it's pretty. It's clear that in the end you still have a time series which you can look at a variable and you know what it is. It is a specific. Okay, it is a specific time frequency. In this case, in this case, their names are just F1, F2, frequency 1, frequency 2, but this could be, say, 40 hertz, right? So if I'm able to extract a logical formula out of this, the formula is going to say this frequency, like this 40 hertz frequency, is not only correlated with COVID, but I can give a temporal pattern in terms of an interval temporal pattern in terms of these frequencies that sort of characterizes, implies COVID negativeness or positiveness. Okay. Also, because this data is much. Wait. Yeah. Okay. So here I'm showing only the cough results because, yeah, 3 negatives and 3 positives. Sorry, the cough recordings, and but I also have breath. So and breath has many points. So the algorithm is not going to accept a data set that is this big. So once again, I downsize. You know, it's a toy example. So let's say at 8 points. I think we played with 20 to 30 to maybe 50 points in our real world in our daily experiments. So then they look like this. Still okay, and I'm gonna do the same that I did earlier. Actually, I just, okay, yeah, this is something new. So if I don't say, if I don't tell the algorithm to use to use a specific set of relations, it's going to fall back to, at least in the temporal case, to interval logic. But maybe I would like to, because interval temporal logic has 12 relations, but some of them are semantically similar. There are pairs of relations that are closer together. For example, the later relation, which tells me like later in time, is kind of close to the after relation, which means I have an interval which starts where I end. So for both reasons of, I mean, I can choose a language where I join these two. So I join these two relations. So I group some relations together, and I have a smaller subset which is still complete. And it partitions and between two any intervals, exactly one holds out of this. And I don't know, I could choose to do this because that's the kind of reasoning that I want to use. I don't want to distinguish that from that. Okay, so in this case, yeah, just showcasing this. Okay, so the real way that you would do experiments, as we mentioned, is not to train a single tree, but to train, say, 10 on different training test splits. So this is what I'm doing here, and I'm using the standard MLJ framework, which is Julia's machine learning framework for machine learning. The average accuracy is about 67 in this example. This is how it distributes throughout the 10 different cross-validation folds, cross-validation splits. So then let's say, okay, out of these 10, I can look at the models that were trained, and you see that I found a way of hiding it earlier because we didn't know what modalities were. But it's the same earlier when I trained a tree, it was a multimodal tree with just one modality. But yeah, if I inspect a tree now, I'm going to expect that some decisions are made on the second frame, that is by looking at the breadth time series, and some others on the cough. And as Guido mentioned, I mean, the semantics for a tree is always that you do some conjunctions along the way if you want to understand what characterizes a certain, what is the formula associated with that characterizes all of the instances that reached a point. So ultimately, when I go and collect my rules, each rule is going to have a part that is true on the first modality and a part that is true on the second modality. These formulas cannot be checked on standard instances that we've seen so far, but on multimodal instances and on multimodal datasets, okay? Or at the logical level on multi-logisets. So we lift all of these concepts, and what we are actually learning are these objects which we call multi-formulas. By the way, I think you can kind of get a feel that these trees look the same, so it feels like at least in size, okay, and okay, maybe that's not the right point to make, but for example, it is very often the first split is on the fourth variable of the breadth frame. 1, 2, 3, 4. So that seems okay. One was not, but that may be something that characterizes the data set itself throughout any split that you can make. So maybe it's picking up. I mean, it's consistent in a way. Okay. So I want to evaluate I've already evaluated my algorithm by considering the average accuracy across the folds. But I also want to look at the rules, because maybe a tree is not that good, but maybe there are rules that are, you have some rules that are really good and some rules that are not. That could be the case. So let's look at the rules and evaluate them on the test set. So let's see. Here, okay, so for example, let's gather all of the rules that were mined across the 10, from the 10 trees. And yeah, I'm going to have many rules. I mean, some rules for the negative class, some for the positive class. Okay. Each rule is associated once again with some information that I'm going to use to compute some metrics. So evaluating rules is actually there's literature on it, but we're going to stick with two simple metrics that are the coverage, how many instances in the test set does my antecedent, my formula that I need to check apply, and my confidence, which is my precision, the percentage of correct classification that I give. These two are usually, well, we would like to have rules that have a high coverage and a high confidence, right? In general, they do not correlate. But here, for example, if I take the rules and I sort them by coverage, I find that. So let's stay here. So this data set has 198 instances, and I've done a tenfold cross-validation, which means that my test sets have about 20 instances, so 10 belonging to a class and 10 belonging to the other. So if we take, for example, this has coverage 0.45% because almost half of the test instances, for almost half of those, the rule applied, which doesn't mean that it gave a correct answer, right? But it gave a correct answer in 78% of these cases. I guess one could argue that, by brute forcing, I'm just brute forcing. I'm gathering all of the rules from the trees, and I mean, this doesn't guarantee, it's not the correct statistical way of evaluating that, right? And that may be right. So that may be right. So yeah, I guess what we really want to do is to look at this and see if they capture similar patterns, okay? At least each one of these had like a high confidence in test, which means that I wasn't looking at the data that I tested on. So, and if they have something in common, maybe that's the right pattern that tells apart these two classes. So let's take the first 5. As I said, there is one part that applies to the cough, and another one that must apply to the breath if I want to say that this applies on an instance. So, for example, something that I see here is that V4 seems to be really important for, if you look at the 4th variable, which is a specific frequency, seems to be important, seems to be an important variable to look at in the, not this last one, but in the breath frame. So let's look at the first 3 things that I've highlighted. So it looks like if all intervals have that property on V4, that implies positive. This is exactly the same property. It implies positive, and this is the opposite property, because there exists one that has the opposite property. So if at some point this appears in the breath, then you're more likely to be negative. This could be. So the point is, if you know about, there is a lot of literature on how cough and breath sound differently if you have a given respiratory disease, not only COVID. So experts in that field may look at these and they may judge them, correct them, and confront them with their own knowledge. Unfortunately, we never got to do that with this COVID data set, but that would be something that could lead to interesting. Would be interesting to explore. Of course, I can translate them to natural language, blah, blah, blah. Yeah, and also, so I don't, this catch-22, right? It's a set of statistical functions, functions that compute some simple usually simple statistic on a univariate time series, so on a single variable, and I can wrap them, and I can tell the algorithm to use these in conjunction with specific test operators. Okay, so the algorithm is going to use those. I can train a tree, and okay, now in this case they didn't improve the accuracy. But then the atoms are going to look like this, and if you know the meaning of this, which is usually something like the number of something similar to the number of peaks, then even then, if it's still interpretable, you could confront that knowledge with human knowledge. And then random forests. Okay, if I take the code that you've seen above and I just replace model decision tree with modeled random forest, I'm going to do an ensemble. I'm going to train an ensemble of decision trees, and this leads to a higher accuracy. And yeah, as Guido mentioned, if I were to increase the number of trees by specifying, you use 1,000 trees, this is demonstrably, in general, it's going to grow. I don't know how formal are the bounds on this result. Except in the end, you get like a larger model, right? So in this case, you have 10 model ensembles of trees, and one of the directions where that would be interesting to investigate on would be how do you get how do you systematically extract categorical rules from the random forests that you can be sure of how they perform. Okay, so this is for COVID. As an example of other kinds of data that you can fit in this framework that Solid can already handle, albeit in a limited way, we can consider an image classification problem. Actually, it's an image segmentation problem where we have satellite, actually aerial data, and we want to classify each pixel in the data as belonging to, actually this is wrong, not 2 classes but 9 classes. For example, you want to know if a pixel is like a field of lettuce or a field of weeds. Yeah, something like that. So in order to do this, you could, this is what we did. You could sample many pixels from the image, and each pixel is your instance. And you could actually, if you sample pixels, you could train a propositional decision tree. But what you can do with this model framework is you can also look at the you can take a small patch around the pixel, and that's your image. And you can train a model decision tree that performs the same reasoning that we were doing with intervals, but in a 2-dimensional domain, so with rectangles. Yeah, And this makes sense for this specific task because, okay, the algorithm for learning a model decision tree can handle only small images. So this, let's say, this task has properties which make it easy. We couldn't probably approach an image, a generic image classification problem because it has many pixels. You have to downsize in the same way that we did. But anyway, if you do it here, you can extract information. But what logic do you use at the second in a two-dimensional domain? If you take the 13 interval relation, the 13 interval relations, you can combine two of these and get what you could call rectangle logic, right? That has 169 relations, and the relations are like LL, which means I have a rectangle, and diamond LLQ means there exists a rectangle later along this axis and later along this axis with a given property. I'm talking about this relation in a coordinate. This is just one out of 169, right? It's a large number, I would say. But yeah, you can express patterns like in terms of rectangles and interval rectangle relations between them. In this setting with land cover classification, though, you would like to learn patterns that are rotation and flip invariant. Meaning the same image, the same neighborhood of images when classifying a pixel, the central pixel, you would like your model to behave in a way that it classifies a pixels regardless of the orientation of the image that you're fed. So if we learn a pattern like this and I rotate the image, this pattern is not rotation invariant, clearly, right? Because if I rotate the image, this is going to become something, a different relation. But there are ways of deriving from this logic Corsair sets that capture topological aspects, like RCC8, and even Corsair sets like RCC5. So what you do is you take these 169 relations, which are, again, a complete relation set, and you group them into just 8, which have immediate semantics. For example, if you take all of the relations that have a later in them, that is all of the blue ones at the edge of this table, and you group them into one, then what you get is there exists a region which I do not have any overlap with. Like there exists a region that is disconnected with me, but anywhere in the image. Okay, so if I flip the image, that is invariant. It's going to the pattern will. I guess you get the idea. So these are the topological operators: disconnected, partially overlapping, externally connected, like it touches me from outside. So if you think of how these project in a, say, 3x3 patch around a pixel, okay? Yeah, if you take any two rectangles, they are going to either be overlapping or they touch from outside. One is inside the other, touching it or not touching it. It makes sense to use this kind of reasoning, to use this kind of logic for this problem. And by using the same framework, the same algorithm, and just by telling, let me see. Okay, here I have already, yeah. Just by asking the algorithm to use RCC8, I can extract patterns that, say, have this, that use these relations. There's also something that we discovered, which is that so if I don't tell, if I don't suggest to the algorithm that we want to look for, we want to learn a formula that is, there exists globally something. If I don't tell the algorithm that the algorithm defaults to learning those kind of formulas. But in this case, and I don't have it here, but we discovered that it was preferable to learn a formula that was true on the central pixel. That is the one that we wanted to classify. So the framework is this. We have a pixel, we look at the neighborhood. We actually, what we do is we classify the image, but we label the image with the label of that pixel. But the formula that we find is something that is true on the pixel, which makes sense. So you want to classify a pixel in an image, you say something about the pixel, but also that tells something about the neighborhood, okay? Could you do that at the propositional level? You could take the 3x3 image and you could flatten it in a way that it fits into a table. You could do that. Or you can do both and use a multimodal setting, right? So, for example, I can load the data set as a table that has small 3x3 images in the cells. I can flatten it and enumerate all of the values that are in there. I'm going to get a bigger table, and I can use both of them, okay, and learn a multimodal decision trees that sometimes speaks multimodal and sometimes makes decisions according to specific pixels, which, by the way, is limited because if you rotate the image, that is not going to work. But still, that is something that you can do. Yeah. So, yeah, so in this case, in cross-validation, I get a 0.77% accuracy, and I can do the same thing that I was doing earlier. So I can look at the most interesting rules. In this case, I have 9 classes, which means that like earlier, it was easier with a positive and a negative one to see that a thing was true. If you had the rule for a positive, then maybe a part of it was false in a rule for a negative. Here it's not as straightforward because you have 9 classes. But still, the same point applies. If I were an expert in the field, I could look at these, and I could confront them with my knowledge. And this is another example where if we do this systematically with larger data sets by sampling more pixels, you get accuracies that are higher than 0.77, what we just saw.